everybody. Good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of the third module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the FDM and FVM solutions of one-dimensional heat conduction problem subject to essential boundary conditions. So to this end, we shall consider Poisson equation of heat conduction in one dimension subject to essential boundary conditions at both the boundaries. In the next lecture, we shall solve this same problem using the Galerkin finite element approximation using two noded or linear bar elements. Now, we shall show the comparison of analytical and numerical solutions of one-dimensional heat conduction problem. We shall first solve the problem subject to essential boundary conditions by using analytical method, and then we shall compute finite difference, finite volume and finite element solutions, and solution we shall compare. So let us start with the analytical solution first. Problem 1. Solve Poisson equation of heat conduction in one dimension using analytical and numerical. By numerical we mean finite difference, finite volume and finite element methods subject to EBC. The governing equation is K del square T plus Q equals to 0, where K, the thermal conductivity, is 1 watt per meter degree centigrade. Q equals to 1 watt per meter cube. Length of the bar is 1 meter. Temperature at both ends of the bar are 100 degrees centigrade and 50 degrees centigrade respectively. Now first we illustrate the analytical solution for this problem. Given K del square T plus Q equals to 0. This is simplified in one dimension as K d to T dx2 plus Q equals to 0, putting K equals to 1 watt per meter degree centigrade and Q equals to 1 watt per meter cube. It reduces to d2t dx2 plus 1 equals to 0. So let us first show the analytical solution. Here temperature at x equals to 0, this is 100 degrees centigrade, and temperature at x equals to 1, this is 50 degrees centigrade. So we have to find out the distribution of temperature. So by analytical method we shall find out the closed form or the exact solution. We write this equation as d to d dx2 plus 1 equals to 0, or d dx of dt dx equals to minus 1, or differential of dt dx equals to minus dx Integrating once, we get dt dx equals to minus x plus c1. Integrating once more, we obtain tx equals to minus x square by 2 plus c1x plus c2. So this is an expression of a parabola. This c1 and c2, they are arbitrary integral constants. By using the boundary conditions for this boundary value problem, we will evaluate c1 and c2, and then we shall get the closed form exact solution for this particular problem. Implementing the boundary conditions, we have at x equals to 0, T0 equals to 100 degrees centigrade equals to 0 plus C1 into 0 plus C2. This gives us C2 equals to 100. And at x equals to 1, T1 equals to 50 equals to minus half, because x is 1, plus C1 into 1 is C1 plus C2 is 100. We just found it. So from here we obtain C1 equals to minus 100 plus 50.5. So this comes as minus 49.5. So the exact solution for temperature is Tx equals to minus x square by 2 plus C1x. C1 is minus 49.5. So here it comes as minus 49.5x plus C2. C2 is 100. So this is the closed form exact solution of temperature, which is of the form ax square plus bx plus c. So this is the closed form exact or analytical solution So this is the best solution possible for this simple problem subject to essential boundary conditions. Now we solve this problem using the numerical techniques, finite difference method, finite volume method, and the finite element method. We begin with the finite difference method. In finite difference method, we start directly with the strong form. The strong form is given as d2t dx2 plus 1 equals to 0. This is the non-conservative form of Poisson equation. The left hand side portion, this is the first portion d2t dx2. This is the diffusion term, and the second portion plus 1, this is the source term. So this is a boundary value problem, and we say that this d2t dx2 term, this is the diffusion term, and this diffusion is an isotropic phenomenon. It has no preferred direction. So we can discretize this term by using a certain differentiating scheme which does not consider directional bias or directional preference. So if we show the rod here, we consider that this rod is of 1 meter length. This left boundary at x equals to 0, the temperature is 100 degrees centigrade. At the right boundary at x equals to 1, the temperature is 50 degrees centigrade. Now we discretize the domain by using 6 nodes. So for 6 nodes, our first node is I equals to 1. The second node is I equals to 2. The third node is I equals to 3. The fourth node is I equals to 4. The fifth node is I equals to 5. And the sixth node is I equals to 6. Now, when we consider the diffusion term, we have already mentioned that the diffusion term does not have any directional bias. Because of that, we have to use the central difference scheme for discretizing the diffusion term, because the central difference scheme, it does not give any directional bias. It gives equal weightage in both the upstream and downstream direction. Now, if we consider this particular picture here, the distance between two successive nodes, that is the grid size. So we represent it as delta x. So here delta x is equals to 0.5. So we have I, it is varying from 1 to 6. So we have delta x, we have 5 values of delta x. So delta x into I max minus 1, that is 1 unit. So from here, delta x into 6 minus 1 equals to 1. So this gives us delta x equals to 1 by 5 equals to 0.2 meter. So this is a uniform mesh. And then if we think of this governing equation, now we try to discretize this. So d2t dx2 plus 1 written at the discrete node I in the left side, it is also considered for the right side. So we can write this as d2t dx2 at the ith node plus 1 is the source term, which is constant. So its value is same at all the nodes. It remains constant. And then the same thing holds for the right hand side, which is also a constant. So this is 0. Now d2t dx2 at the ith node, we have to discretize. d2t dx2 at ith node, it can be discretized. It can be discretized using first order forward difference, first order backward difference, and second order CDS or central difference scheme. So BWD stands for backward difference. Backward difference. FWD stands for forward difference. It means that for the second derivative, there are 3 possibilities. We can choose either forward difference or backward difference or the central difference. So let us write these expressions first. d2t dx2 at the ith node using the forward difference scheme. So if we have the grid stencil, this structure of grid is known as the grid stencil. This is the ith node. This is the I plus 1th node. This is the I minus 1th node. This is the I minus 2th node. And this is the I plus 2th node. So distance between two successive nodes, that is the mesh size or grid size. In finite difference, we use the word grid size. This is the x-axis. Now, using forward difference, d2t dx2 at the ith node here, it comes as t I plus 2 minus 2ti plus ti minus 1 by delta x whole square plus order of accuracy is first order. So we write it as order of delta x. Now, backward difference scheme for d2t dx2 at the ith node, it comes as ti minus 2ti minus 1 plus ti minus 2 by delta x whole square plus order of delta x. And central difference scheme for d2t dx2 at the ith node, it becomes ti plus 1 minus 2ti plus ti minus 1 by delta x whole square plus order of delta x whole square. It means that for the same second derivative, we have three different expressions by using forward difference scheme, backward difference scheme, and the central difference scheme. Here, we cannot use the biased direction schemes like forward difference scheme or backward difference scheme, because forward difference scheme and backward difference scheme, they are biased towards the forward direction or the backward direction respectively. The central difference scheme does not have any directional bias. If we come to the grid picture, then with respect to the ith node, the forward difference scheme, it contains the nodes I plus 1 and I plus 2. It means that it is showing the forward direction bias. If you go for the backward differentiation scheme, then we have nodes I minus 1 and I minus 2. It means that these are one-sided differentiation schemes. Now, if we go for the central difference scheme, it contains I plus 1, I and I minus 1, where distance between I plus 1 and I minus 1, it is same. It means that the central difference scheme, it accurately captures the physics of the diffusion term, so that we must use the central difference scheme for the diffusion dominated problems, and we should never use the forward difference scheme or the backward differentiation scheme for the diffusion dominated problems. So here the choice of central difference scheme is not governed by the fact that its order of accuracy is 2 as opposed to the order of accuracy 1 for the forward or backward differentiation scheme. The choice of central difference scheme as opposed to the forward or backward differentiation schemes is driven by the fact that the central difference scheme only does not take the consideration of direction, and which is a property of the diffusion phenomenon. So now we have decided that we have to use the central differentiation scheme for discretization of this Poisson equation. We have already mentioned in the previous classes that the central difference scheme in finite difference or finite volume methods, these are equivalent to the Galerkin scheme in the finite element method. So certainly for the finite element method, we have to use only the Galerkin formulation for the diffusion dominated problems or problems governed by elliptic partial differential equations. So there is a correction. This is I plus 2. This is I plus 1 and this is Ti. So this is actually Ti plus 2. This is minus 2Ti plus 1 and this is Ti. So FWD, if I write it here again, d2t dx2 and the ith node equals to Ti plus 2 minus 2Ti plus 1 plus Ti by delta x whole square plus order of delta x. Now we move forward. Here the governing equation in the discrete level, it is d2t dx2 at the ith node plus 1 equals to 0. Using the CDS scheme, we obtain Ti plus 1 minus 2Ti plus Ti minus 1 by delta x whole square plus 1 equals to 0, or we get from here Ti plus 1 minus 2Ti plus Ti minus 1 plus delta x whole square equals to 0. Now this is the finite difference discretized algebraic equation. This is the equation where we have to distinguish between the known terms and the unknown terms. The known terms will be shifted to the right hand side, where the unknown terms are retained in the left hand side. So this is the source term, which is a known quantity because we know the x coordinates. So this delta x whole square we shall shift to the right side, and this term, this comes from the Laplacian operator. So These are the unknown terms or nodal values. So we rearrange this equation as ti minus 1 minus 2ti plus ti plus 1 equals to minus of delta x whole square. So this is known as the finite difference discretized generic algebraic equation at the ith node. So this is FDM discretized generic algebraic equation at ith node, where I varies from 2 to 5. At I equals to 1 and I equals to 6, EBCs are given. So we solve for I equals to 2, 3, 4 and 5. Therefore, we shall get 4 algebraic equations for 4 unknown nodes. Now, if we plot our grid, we have the first temperature is given 100 degrees centigrade. Now we have the nodes here. So this is I equals to 2. So this is T2, this is T3, this is T4, this is T5 and this is T6, where 50 degrees centigrade is given, and this is T1 given 100 degrees centigrade. So these are the unknown temperatures for which we shall write the algebraic equations. Unknown temperatures. Now del square T plus Q equals to 0. This is a linear equation. Since this is a linear equation, the generic algebraic equation is also linear. Now we shall write the equations at the unknown nodal points by putting the values of I. So at I equals to 2, our algebraic equation is Ti minus 1, so T2 minus 1, so it will be T1 minus 2T2 plus T3 equals to minus delta x whole square. But T1, it is a known quantity, it is given as 100 degrees centigrade. Known terms are shifted to the right side, and this is the boundary condition which contributes to the right side. So we write this equation as minus 2T2 plus T3 equals to minus delta x whole square minus T1 equals to minus 0.2 whole square minus 100 equals to minus 100.04. So this is source term, this is EBC. So this is the equation at node number 2. It means that when we write the algebraic equation at node number 2, contributions come from node 1 and node 3. But since we know the solution at node 1, this contribution shifts to the right hand side. So the algebraic equation at node 2, it consists of unknown quantities T2 and T3. Similarly, when we go for I equals to 3, we write the governing equation in the algebraic form at the third node. In that case, our temperature at third node, it depends on the temperatures at nodes 2 and 4. Since this is an elliptic partial differential equation, we have to use an implicit formulation, and what we are doing in finite difference method, this is exactly an implicit formulation where we have to write all the equations and then we can solve the matrix equation system. In this case, we have already introduced that in the implicit scheme, the global matrix equation system will never be of diagonal type. In finite difference method, there is no concept of local. The matrix equation which we get at the final stage, that is by default the global matrix equation system. Now we write the algebraic equation at node 3. So here we write at I equals to 3, the algebraic equation is ti minus 1, so it will be t2 minus 2ti, so it will be 2t3 plus ti plus 1, so it will be t4 equals to, the generic form was minus delta x whole square, so this is minus delta x whole square. So we get from here t2 minus 2t3 plus t4 equals to minus 0.2 whole square equals to minus 0.04. Similarly, for I equals to 4, we have t4 minus 1, t3 minus 2t4 plus ti plus 1 means t5 equals to minus delta x whole square, or t3 minus 2t4 plus t5 equals to minus 0.04. Now we are left for the last node. For I equals to 5, we obtain t5 minus 1, t4 minus 2t5 plus t6 equals to minus delta x whole square. Now this t6, this is an EBC node, so this will be shifted to the right side, so we can write it as t4 minus 2t5 equals to minus delta x whole square minus t6, we get here, this is minus 0.04 minus 50 equals to minus 50.04. Now we write all the algebraic equations together, all the discretized equations are written together as minus 2t2 plus t3 equals to minus 100.04, minus 2t2 plus t3 equals to minus 100.04, t2 minus 2t3 plus t4 equals to minus 0.04, t3 minus 2t4 plus t5 equals to minus 0.04, and finally we are left with t4 minus 2t5 equals to minus 50.04. So these are the examples of coupled or simultaneous algebraic equations that are obtained using an implicit formulation. Whatever the steps we have followed here, this correspond to an implicit formulation, and we got a system of algebraic equations that is of not diagonal type. In one equation, we have many unknowns. That is a feature of the matrices that are outcomes of implicit formulations. Now, these four equations, we can write them in a square matrix form, which will be of size 4 by 4. So, here our unknowns are T2, T3, T4 and T5. For the first equation, our terms are T2 and T3. So we have minus 2T2, so it is minus 2. For T3 it is 1, and we don't have any contribution from T4 and T5, so these terms are 0. The right hand side will be minus 100.04. Now, the second equation, in this case, T2's contribution is 1, so it is 1. T3's contribution is minus 2, so it is minus 2. T4's contribution is 1 and T5 does not exist, so T5's contribution is 0 and the right hand side is minus 0.04. For the third equation, T2 does not exist, so its contribution is 0. T3 contributes as 1, T4 contributes as minus 2 and T5 contributes as 1. Then the right hand side is same as minus 0.04. Since the nodes 3 and 4, they belong to internal nodes, the contributions from boundary condition do not affect them. So the only source term they are contributing to this right hand side of the algebraic equations at nodes 3 and 4, whereas at nodes 2 and 5, they are being near the boundary nodes. Their load vector is contributed by the essential boundary conditions at the first and the last nodes respectively. Finally, for the last algebraic equation, our T2 and T3, they do not exist, so their contributions are 0. Then contribution from T4 is 1 and contribution from T5 is minus 2. So we can rearrange or we can rewrite this matrix equation system here again as 2, minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2. Just to make that diagonal term positive, we have multiplied by minus 1 on both sides. So we have T2, T3, T4 and T5. So this is a 4 by 4 square matrix equation system. This is a 4 by 1 vector and this is a 4 by 1 vector. Here the right hand side load contribution was minus 50.04. So here the sign of the right hand side load vector, it will change. All the quantities, they will be positive. So now it is 100.04, 0.04, 0.04 and then finally it is 50.04. So this is the FDM discretized matrix equation system AT equals to B, where A is the coefficient matrix, B is the load vector and T is the degree of freedom vector. Okay, now if we look at this matrix, we can see that this matrix is symmetric, this matrix is diagonal dominant and this matrix is also positive definite. Positive definite we have already discussed in the first lecture of this course. So we have already shown there that matrices coming out of Laplace or Poisson type of equations, they will satisfy the positive definiteness condition of a symmetric matrix. So the matrix A, the 4 by 4 coefficient matrix A is banded, symmetric, positive definite, sparse and diagonal dominant. When we say that this is a banded matrix equation system, we note that in this case we have three diagonals or the matrix is tridiagonal. So, if we look at the matrix equation system, it has 3 diagonals. The remaining terms are all 0. So, we say that this is tridiagonal matrix equation system. A direct equation solver known as Thomas algorithm is the best solver for solving the unknown quantities in a tridiagonal matrix equation system. Thomas algorithm or the tridiagonal matrix algorithm, in brief it is written as TDMA with this acronym, is the best solver for a tridiagonal matrix equation system. This is a direct linear equation solver with operation count of the order of the size of the matrix. So, the number of addition, multiplication, division and subtraction, this order during the solution process gives us the operation count of direct matrix equation solvers. So, for a square matrix equation system of dimension n by n, the operation count for Thomas algorithm or TDMA is of the order of n. Solving by the Thomas algorithm, the solutions which we get for this case, these are T2 equals to 90.08 degrees centigrade, T3 equals to 80.12 degrees centigrade, T4 equals to 70.12 degrees centigrade, and T5 equals to 60.08 degrees centigrade. The governing Poisson equation in heat conduction is given as K d2T dx2 plus Q equals to 0. When we discretized this equation by using finite difference method, our discretized equation was like using FDM discretization. We got it like T I minus 1 minus 2Ti plus T I plus 1 equals to minus Q by K into delta x whole square. This is the ith algebraic equation. So there is a mesh stencil. Part of this I am showing here. This is the ith node. This is the I plus 1th node. And this is the I minus 1th node. This is the x direction. And the grid size in finite difference method. This is delta x. And this is strong form of one-dimensional Poisson equation. This particular form is known as the non-conservative form. Now, in this expression, Ti minus 1 minus 2Ti plus Ti plus 1 equals to minus Q by K delta x whole square. This is the ith equation. The coefficient of the ith term, it represents the diagonal of the matrix equation. Okay? So, this represents the diagonal term of the matrix in the ith equation. Similarly, the coefficients of Ti plus 1 and Ti minus 1, they respectively represent the super diagonal and subdiagonal terms in the matrix equation system. Okay, so here the coefficients are both 1. So this coefficient, which is 1, the coefficient 1 is the super diagonal term of the final matrix. Similarly, here the coefficient 1 is the subdiagonal term in the final matrix equation system. AT equals to B. Now here we have only 3 terms present: Ti minus 1, Ti and Ti plus 1. So we understand that the coefficients of all these terms, they correspond to 1 diagonal. It means that the resultant matrix must be a banded matrix. In this case, since we shall get 3 coefficients, namely 1, and minus 2, the coefficient matrix will be a tridiagonal matrix. Now we go for the solution of the same problem by using the finite volume method. Okay, so whatever I have discussed here, this is for the finite difference part. So in the finite volume method, which is a variational method, we have to integrate the governing equation. So we don't start with the non-conservative form of the governing equation. We represent the non-conservative form of the governing equation in the strong conservative form, and then we perform the integration. For FVM, non-conservative form of the governing equation is represented in strong conservative form, since FVM is a variational method and we integrate the strong form. So our given equation was k d2t dx2 plus q equals to 0. This was given non-conservative form. We represent it as d dx of k dt dx plus q equals to 0, strong conservative form for FVM application. Now, this is the domain over which the governing equation is valid. So d dx of k dt dx plus q equals to 0 on omega. So let us take, this is the omega, this is x equals to 0, this is x equals to 1. Boundary conditions are T0 equals to 100 degrees centigrade and T1 equals to 50 degrees centigrade. Now, in the finite volume method, we have to integrate the governing equation. We shall follow the method of weighted residuals. So here, our residual is d dx of k dth dx plus q. Using MWR statement, we have integration over omega WR d omega equals to 0, which is cell for finite volume, that is an element in finite element method. These cells and elements, they are generated after the domain discretization or the mesh generation. Now, the weighted residual statement in the global sense, it is valid also for the weighted residual statement as element level equations. So if we consider that this is a cell and then these are the cell boundaries, so we say that this is a finite volume cell. The center of the cell, it occupies the node of interest. We say that point capital P represents the node where we write the equation. It has two immediate neighbors. These neighbors are denoted by symbols capital E in the east direction and capital W in the west direction. The cell faces are denoted by the symbol small e and small w respectively, and the cell dimension is delta x. This is the mesh size. Now in finite volume there are two approaches of mesh generation. We say that we can use the cell center method and the cell vertex method. The picture which I have shown here, that is following the cell center method. It means that at the center of the cell we locate the degree of freedom. So first we show the mesh generation here for the given problem. We use 6 nodal points as we have done in the finite difference case. So node 1, node 2, node 3, node 4, node 5 and finally the node 6. This is the x-axis. At node 6 we know the solution as 50 degrees centigrade. At node 1 we know the solution as 100 degrees centigrade. Now here we are showing one representative cell. So this is the finite volume cell corresponding to the cell center approach. So this point 3, it is equivalent to point capital P in this lateral picture. Now after we generate the mesh, we can go for the MWR statement at the element level. So MWR at cell level is integration over omega e WRX d omega e equals to 0. We already discussed that finite volume method is a special case of finite element method. In finite volume method, the weight function value is unity. So in FVM, Wx is a constant and it is always unit valued. So we can write it as integration over omega e 1 into d dx of k dt dx plus q and d omega e equals to dx equals to 0. This gives us integration over omega e d dx of k dt dx plus q dx equals to 0. This we can simplify as integration over omega e d dx of k dt dx plus integration over omega e q dx equals to 0. We can take k and q as constants. The element or cell omega e, it has boundaries, east boundary and west boundary. So the integration extends from the west face to the east face. So this can be simplified as integration from x west to x east differential of k dt dx plus q into integration over dx from west face to the east face equals to 0. So integrating we get k dt dx from the west face to the east face plus q into x from the west face to the east face equals to 0. This gives us, so this is obtained after integrating. This gives us k into dt dx at xe minus k into dt dx at xw plus q into x east minus x west equals to 0. So if we replot the region of interest, so here this is our point P, this is the node point P, this is the mesh size delta x. So this is the east face, this is the west face. So this neighbor was capital E and this neighbor was capital W. So these distance between the nodes, that is also delta x. Now this k dt dx term at the x east face, it can be written as k into Te minus Tp by delta x minus k into Tp minus Tw by delta x plus q into delta x equals to 0. This x east minus x west, this is the mesh size. So this can be written as Te minus Tp minus Tp plus Tw equals to minus q by k into delta x whole square. So this is the finite volume discretized algebraic equation for a simple equation in one dimension, and then this can be further simplified as Te minus 2Tp plus Tw equals to minus q by k into delta x whole square. Now we can indicate the pth node as the ith node in correspondence with the finite difference method. When we deal with one-dimensional problems, it will be shown later that finite difference, finite volume and finite element, particularly for this heat conduction problem, it gives us the same matrix equation system and accordingly it gives us the same solutions. Then we can make a correspondence as Ti plus 1 minus 2Ti plus Ti minus 1 equals to minus q by k delta x whole square. This is exactly the same equation which we obtained in finite difference method. Exactly the same equation as FDM. So denote P by I, E by I plus 1 and W by I minus 1. So if we do this, then we get the same algebraic equation as we got for the finite difference case. Now our unknowns are at nodes 2, 3, 4 and 5. Okay, so if we draw the mesh again here, these are the nodal points. So this is the second node, third node, fourth node, fifth node. At sixth node we know the solution. At the first node we know the solution. So these are the DOF nodes. So when we start with I equals to 2, I is varying from 2 to 5. I equals to 2 gives, and our algebraic equation was Ti minus 1 minus 2Ti plus Ti plus 1 equals to minus q by k delta x whole square. Now q equals to 1 unit, k was also 1 unit, so it reduces to Ti plus 1 minus 2Ti plus Ti minus 1 equals to minus delta x whole square. Now the mesh size delta x is 0.2. So here we are getting T1 2 minus 1 minus 2T2 plus T2 plus 1 equals to minus 0.2 whole square. So we get T1 minus 2T2 plus T3 equals to minus 0.04. This gives minus 2T2 plus T3 equals to minus T1 minus 0.04 equals to minus 100 minus 0.04 equals to minus 100.04. T1 is known from EBC. Now for I equals to 3, we can write T2 minus 2T3 plus T4 equals to minus 0.04. For I equals to 4, we can write T3 minus 2T4 plus T5 equals to minus 0.04. And finally, for I equals to 5, we get T4 minus 2T5 plus T6 equals to minus 0.04. Now T6 is given as 50 degrees centigrade. This gives T4 minus 2T5 equals to minus 50 minus 0.04 minus 50.04. Combining all these algebraic equations, we construct the matrix equation system. In finite volume also, there is no concept of the local nodes and local equations. All the equations we have written, these are the global equations. So the matrix which we shall construct now, that is also the global matrix equation system. We combine all these equations to get combining the algebraic equations, we get minus 2, 1, 0, 0, 1, minus 2, 1, 0, 0, 1, minus 2, 1, 0, 0, 1, minus 2. This is a 4 by 4 matrix. Then we have T2, T3, T4 and T5. The load vector in the right hand side, these are all negative quantities, minus 100.04, minus 0.04, minus 0.04, minus 50.04. So this is exactly the same matrix equation system that we have obtained using the finite difference discretization. So here we know already the solution. The temperatures obtained from here, T2 equals to 90.08 degrees centigrade, T3 equals to 80.12 degrees centigrade, T4 equals to 70.12 degrees centigrade, and finally T5 equals to 60.08 degrees centigrade. So for a simple one-dimensional problem, the finite volume and finite difference method, they lead to the same solution. Now, once the finite element solution is obtained, then it will be found that even the finite element solution also matches with the finite difference and finite volume solutions. In particular, all three methods, they give us the same matrix equation system, and accordingly we get the same solution. Therefore, for 1D Poisson equation of heat conduction, FDM and FVM provide identical solutions. Now I conclude today's class. In today's class, we have shown the FDM and FVM solutions of Poisson equation in one dimension. We have solved Poisson equation of heat conduction in one dimension using analytical method along with numerical FDM and FVM methods. All the solutions match with each other. For 1D heat conduction, the coefficient matrix tridiagonal, symmetric and banded. In the finite volume discretization, the temperature gradient was discretized using the central difference scheme for the first derivative. It means dt dx at the east phase equals to Ti plus 1 minus Ti by xi plus 1 minus xi equals to T east minus Tp divided by delta x plus order of delta x whole square. Okay, so this is the CDS for first derivative. Here we list the references for today's class. The text by Professor Patankar. This will be useful for the finite volume portion, and for the finite difference portion I recommend the book by Professor J.D. Anderson. Thank you very much for attending today's lecture.